Yep, my screen is sharing. Okay. Hello, everyone. My name is Gabriel, and together with my teammates Hightem, my name is Clinton, and together with my teammates Gabriel and Hightem, today we'll be talking about digital image correlation and Poisson's ratio.
Our goal in this lab was to use GOM correlate to measure the strain from the digital image correlation under the tensile loading, and to obtain the strain results, we recorded the axial and transverse strain and found the Poisson's ratio and compared it to the textbook values to calculate percent error.
So for what Poisson's ratio is, it's material property that describes how the material change shape when it is stretched and compressed, or in other words, in axial and lateral direction. It's defined by its negative ratio between the lateral and the axial strain. And when the material is pulled, it gets longer in one side and thinner in another direction. And that behavior follows Hooke's law in the elastic region.
What digital image correlation is? So basically, it is an optical method that tracks speckle pattern on the material surface, and it compares the before and after images to calculate the difference in how the sample is stretched. Digital image correlation is perfect for small elastic tests because it converts pixels movements into strain.
So to prepare for this experiment, we used three different material samples, copper, aluminum, and polymer, and we measured the average gauge length and width, and then we used the consistent thickness of 0.05 for all of the samples. And before we started recording, we preloaded each of the samples to up to 3 pounds to remove any slack or to strain it out and to zero it out.
So we used GOM Snap to record the test. It captures multiple frames at so we took each video, we took a 17 hertz at 120 images, and we did that while we were adding the load and to record the displacement.
So for the GOM correlate, we imported our video into GOM correlate, and then we defined our scale and parameters, and then we applied it in a 3-to-1 alignment, which matched the coordinate axis to the sample. And for this, we used it to compute our epsilon x for axial strain and epsilon y for transverse strain. And in the image, you can sort of see an example here of our epsilon x and our epsilon y for our material sample.
All right, so on the left is our epsilon y data, is our epsilon x data, which is positive correlation. In the middle is our epsilon x data, which is negative. And we made two columns of each component for each column and averaged all of the recorded components and made two tables, then which we then used to plot some graphs. And here we have three graphs of all the data. We applied a linear regression model to find the slope, which is the absolute value of is the Poisson's ratio, and we have the literature values, the measured values, and the percentage shares at the bottom. Right.
And for the aluminum sample, we used another group's.
All right, next. All right, so our aluminum data was from the CTE group. To let you know, our copper and polymer data was all recorded by us. So the calculated Poisson's ratio for aluminum and polymer, or copper and polymer, followed the textbook data, with the highest margin of error being for copper, which was 10%. And for nylon, it was less than 1%. We determined it to be nylon 6.6 based off of a table of polymers. And our aluminum data, despite following the usual trend for Poisson's ratio, was off by a magnitude of 172%. This could be due to the grips not being parallel with each other. The preload is improper, so we may not have preloaded it as correctly. Maybe we put too much, maybe we put too little weight. And the clamps are meant to be tight, meaning that nothing should be sliding in there or, spinning or right. Next. There we
So
So,
overall, the
oh,
digital image correlation worked well for finding the Poisson's ratio. When done correctly, the data closely matched the textbook values. With more samples, we would have been able to gather far more accurate data and more consistency.
so for future work and recommendations, especially if we do this again, keeping our cameras further out, so that we can more accurately, capture the material. Setup made hard to crankshaft and apply force. So our setup, very important. Making sure everything is aligned properly so that we don't get any, more noticeably human error when working with the different samples, pre-checking all of our clamps and our gauges, and also just collecting more sample data so that we can, collect the best average out of all the data we have to give us a more accurate data.
We use data from MatWeb and also as well as the CTE group for the aluminum there for comparison. And that was all. Thank you so much.
Thank you very much.
just done the recording.